The next aspect that it is very important in analyzing nonlinearity, it is the compression. So as we mentioned before, the value of c in this polynomial is always negative, and that basically means that the fundamental, when it is amplified, will decrease in amplitude for large input signals, and that phenomena is called compression. It's called compression, and then the signals will suffer compression when there is a high level of input. And we can define some figure of merits. We defined the first 1 dB compression point, and then as a function of a and c, we have that this compression point happens at square root of 0.145 a divided by c. And we can also define a 3 dB compression point. We have the following expression also as a function of a and c. So what does it tell us, this 1 dB or the 3 dB compression point? So what is happening here is that the system is basically leaving the weak nonlinearities, and then it is becoming very strong nonlinearities. Basically it is starting to clip the signal. So it is a very important figure of merit. It has very strong implications with the signal that we can amplify, because basically the amplification stops being linear when we are reaching the 1 dB compression point. So sometimes we have specifications for compression points, especially in, for instance, in radio applications. Likewise, we have a concept of the intercept points. Normally, there's a figure of merit in radio design, and we have actually two different definitions for these intercept points. We have when we inject a singleton, so we have our input, it is a singleton located in omega 1. Then we saw that it will produce, if this is the input, we'll have an output. There will be an amplified output in omega 1, and there will be some harmonics. So for a single tone, we have that the IP2 is defined as 2 times A over B. And what is this intercept point? Well, if we increase the power, the input power, we see that the fundamental, it is growing. Okay, it is growing with one slope. The second order, that it is quadratic, it is going to grow faster. The slope, it is twice. And the third order naturally will grow much faster because it has a cubic dependence. And if we extrapolate, in these in dBs, we will see that they can be plotted as lines that will cross at some particular point. And these points are the ones that we are calling the intercept points. And they are figure of merit. So the higher the intercept points, the more linear the system is. So we can think that a system that intercepts, they have intercept point very high input levels, it is much more linear than one that intercepts at very low levels. So we typically use this in radio applications, and also, as mentioned before, in radio application it is very important to see what happens when we have two tones. Okay, if this is the input, then we will have the output here, and then we will have tones at the same frequency, and then we will have third order intermodulation, and we will have also second order intermodulation happening, and then the Same, we can do the same calculations, and for the second order intermodulation we have different equations that can relate exactly where the intercept points are located. Okay, so those figure of merit can be very important, can be specifications for our design. Now we're going to talk about a very important topic, is that what happens when we add feedback to a nonlinear system. And yeah, for that we have to study the differential error to gain ratio. And what is this? If we have our loop gain AB, we can do very similar treatment that we did for the differential gain. So we can find an error in the loop gain. An error in the loop gain will be an excursion from the operating point ABQ, and then this excursion AB minus ABQ, we can express it as a percentage or as a quote. So that will be our basically our error, and then we have our physics expression here. Now in a negative feedback system, the closed loop gain, we can do exactly the same. For the closed loop gain, we can express the error in the closed loop gain as a quote, or as a percentage if we multiply by 100. And yeah, at the same time we have the expression for the closed loop gain equal to AF asymptotic gain multiplied by this factor that depends on the loop gain. Okay, so then if we derivate this expression and to the if we differentiate the closed loop gain to the differential of the loop gain, and then we start arranging a little bit the math, then we will come to the very interesting conclusion. We will come to the following expression, in which the differential of the closed loop gain divided by the closed loop gain, that is a percentage. This is the percentage that the closed loop gain has moved with respect to the closed loop gain. That means the error that I am having in my closed loop gain, it is equal to the error that I have in the loop gain divided by the total loop gain. So this is very interesting. This is a very interesting conclusion. The error in the closed loop gain can be expressed as the error in the loop gain divided by the total loop gain at the operating point. So typically this is very large, so we can just in most of the cases we can just forget this one, and then it happens that the error it is the differential error, we call it D, the differential error. It is basically divided by the total loop gain, that it is a total gain. We can consider this a figure of merit. This is the error that we will produce the distortion, the nonlinearity, and the loop gain, on the other hand, it is going to damp this error, this nonlinearity. So if we divide this differential error and the gain, we have a figure of merit, and then we can use this differential error to gain ratio as a tool to study different stages and decide which stage is more linear than other. And when I mean which stage that I use in a negative feedback loop. So there are some stages that will contribute more with distortion and more with gain, and then just by dividing the differential error and the gain that they have, we can make very interesting comparisons. Now, before going to study different stages, I can immediately see that common source stages have the largest gain. So the ABCD parameters for the common source stage are very low. They have the largest gain. Then they will immediately contribute more to the loop gain. So they will have more better damping of the differential error than other stages. So that is what we say, that in most of the cases the preferred stage to put at the output of an amplifier, the last stage, it is a common source, because they provide a lot of gain that will damp the differential error. Okay, so now that we have found the figure of merit, the differential error divided by the gain that the stage has, then it comes to the following question: which stages are suitable as output stages? So we have postulated that already that the common source stage is the best because it provides a lot of gain, but now we are going to show it formally. So we are going to analyze the differential gain, or also sometimes we call it the distortion to gain ratio, because the differential gain, it is just introduction distortion. We are going to analyze it for different stages, and then for doing that we take our stage under test and under study as an ABCD parameter, and then we connect it with a voltage source and towards a load, voltage source and our source impedance and the load impedance. And then if we do that, we can extract the total gain. The gain, it is output voltage divided by input voltage, and then once we express this as a function of the ABCD parameter, we have the following equation here. And now if we extract the error, the differential error, basically an excursion of the gain from its operating point divided by the gain at the operating point, then we have the following expression. And then if we divide this differential error to the gain and manipulate a little bit the expression, then we will have something very, very interesting, and it is that the differential error to gain will depend on these deltas of the ABCD parameters, and it will also depend partially with the source and the load. In all cases, if the ABCD parameters increases, then the differential error to gain ratio it is worsened. Okay, so larger delta ABCD will result in a higher level of distortion, because of then our figure of merit gets degraded. So in other words, then again we come back to the observation that we had before. The common source stage is probably the best alternative from the differential error to gain ratio, because it has a equal to 0, no, b no equal to 0, but E is close to 0, B is close to 0, C is close to 0. So it has lower values for the ABCD parameter, so that it is the best option from the linearity point of view. Now, there are situations in which we have impedances at the input of the output of our stages, and then it is useful to study what is the impact of this impedance. So what happens when we add impedance at the input? So when we add impedance at the input of our stage, of our amplifying stage, what happens is that we add this impedance zeta here and impedance zeta here. What happens is that the factor C, the transimpedance, it is increased. So it is increased, and then the current gain also it is affected. So these factors increase, which means that the differential error to gain, it is degraded. The same if we have it in series instead. We have that the A factor will increase, meaning that the voltage gain will be degraded, and also the transconductance gain will increase, meaning that the transconductance will be degraded. The B will be degraded. So two parameters will be degraded in the series resistance, and two parameters will be degraded in the zeta when we put the zeta as a parallel. So it is not a really good idea from the linearity point of view to add impedances at the input. Now, what happened at the output? Maybe we might think that adding passive components that are very linear will linearize the system, and it turned out that actually not. If we add parallel impedance at the output, what happens is that the voltage gain will be reduced, meaning that there will be less gain in the loop, and the differential error to gain will be reduced. So same with the transimpedance parameter, C, it will be increased, meaning that the transimpedance gain will reduce. If we put it in series instead, the same story. There are two parameters that will be degraded, and then the conclusion here is that the differential error to gain ratio degrades in all the cases. So it is not a good idea to add impedances at the input or at the output of a block, because when we put this block in a negative feedback system, what it happens is that the additional impedances that we add, they will only degrade the linearity. Now, sometimes we have to do this, and one case that we have studied a little bit of, we have talked a little bit, is that when we have to do compensation, maybe we need to add some passive component to do the stabilization, but any other cases, it is not a very good idea, because the linearity will be degraded. Now let's study. Let's focus a little bit on the blocks that we have studied before, and then we have the common drain and common gate stages. And then we have that these blocks have one parameter that it is close to 1. And even though these parameters are quite linear, in the case of the common drain, the voltage gain is approaching to 1, and in the case of the common gate, the current gain is approaching to 1. The total differential error to gain ratio is reduced, meaning that their contribution to the loop gain is reduced, and then they are not optimal to be used as an output stage. So we don't say that we cannot use these stages as output stage. It is just that the linearity will be affected. So let's be a little bit instructive. We have, for instance, a common drain amplifier is a buffer. It's working like this, and then if we have, let's suppose that we have a common source amplifier with can be MOS or bipolar transistors. Let's make it with MOS transistors. So if we have the following situation here, now let's think for a second. Signal swing at the output. I mean, we have said that there is a large signal swing at the output of the last stage. In the case of the common drain amplifier with a voltage gain of approximately equal to 1, we will have about the same signal swing happening here. And that is a signal swing that will appear at the output of the first stage, and that is also going to be stressing the linearity of the first stage. Okay, and think about this. The output transistor will see very large signal swings both at the input and on the output. So, and in addition, it's going to be stressing the output. The output voltage swing of the first stage is going to also to be affected, and then introducing nonlinearity. So, this is one of the issues of using buffer, and it can be a voltage buffer, or it can also be a current buffer at the output. So what the difference, for instance, if we have let's see, we have something like this instead. Okay, we have let's say the following amplifier chain, and then if we have the same signal swing here, the signal swing at the input of the last amplifier will look like this, and at the input of the second amplifier it will look like this, and then we go to the input of the first amplifier, it will look much more smaller. So think for a second, the signal swing that we see at the input of the last stage is much smaller, so it's going to stress less the linearity requirements of the last stage, and then also the second stage also will see less signal swings around its voltage than less the first one. And in addition, I mean, when we connect this towards the input, there will be much more loop gain than, for instance, in this case, if we do the same, we put the feedback here, so we will have much more loop gain in the case down. We will have other problems here, of course. There will be stability issues that we have to solve, but we will deal with those ones in a different lecture. Then there is also the alternative of using passive components to linearize the stages, and we have seen, for instance, the series stage here, and the shunt stage with the shunt resistance here. And we should discard these ones immediately, because all the ABCD parameters are just increased when we add these impedances, and then the differential error to gain ratio is just reduced. So it is not a good idea to use such stages as the output. So let's put as an example. We have a series stage at the output. Let's say that it will look something like this. We can have it like this. We can see almost directly that this stage has a disadvantage. So when we have some current at the output IDS, the presence of the series resistance here at the output, this series resistance, it already consumes some overhead voltage that it is going to reduce the amount of voltage swing that is available at the drain to source of the transistor. So just its presence creates this voltage drop, and then it already reduced the voltage swing, the possibility of swinging around the drain to source. Okay, just by that reduction, it is introducing some nonlinearity problem. It is just limiting the linearity at the output of the transistor, and so in general, it is not a good idea to use series and shunt stages. Now we talked a little bit about balanced stages before. Here we touch them again. we have two balance stages that are exactly the same. ABCD is exactly the same. They can be two transistor bias at the same current, the transistor of the same size. And if each transistor provides a gain that can be modeled with this polynomial, then when we connect it as a balanced configuration, for instance like a differential pair, then we have that the input voltage can be modeled as having half of the voltage going to one device and the other half going to the other device. When we have a differential input, and then we see that the one input it is going to process positive voltage, half voltages, and the other half negative voltages. And then when we square the even components, so when we raise to the square or raise to the fourth, and we take the signal differential, we will be subtracting all the even order distortions. And then the only thing that will be remaining are the odd components. So just by using the balance configuration, then we managed to cancel or attenuate strongly the even order distortion. Now we cannot really get rid of completely of the even order distortion because we cannot in practice have perfectly matched devices, something that we are going to touch later. Finally, we have to take in consideration the dynamic nonlinearity. And dynamic nonlinearity is coming from components that have memory, and those components are basically capacitors. Those also contribute to nonlinearity in different ways. And then one of the very important details is that many of the capacitors inside a transistor are intrinsic capacitors that depends on the biasing point, and since their value depend on the biasing points, they are very nonlinear because these values are going to be changing depending on the voltage swings, so they will be all the time being changing their value. So we have the gate to bulk capacitance, gate to source capacitance, bulk to source capacitance, drain to bulk capacitance. Those reverse bias diode capacitance are nonlinear capacitors, and then they are going to introduce nonlinearities when the circuit is in operation. We have already studied the transconductances. The transconductances are nonlinear, but those ones we can extract with the static nonlinearity. Resistance also, RDS, the output resistance is also nonlinear, but these three, they appear already in the static nonlinearity. Special mention, CGD is an overlap capacitor, but when we connected the common source amplifier, then we have to be careful because under some conditions this capacitor suffers Miller amplification, and then the transconductance is a very nonlinear parameter in the transistor. Then the capacitor itself, it is an overlapping capacitor, is a passive capacitor, very linear. The Miller capacitor, it is a very nonlinear, can introduce a lot of nonlinearity. So these capacitors, they are embedded in the transistors, and then naturally they are going to appear in the positions of the poles and the zeros, introducing nonlinearities in the transfer function. Now, most of the weak nonlinearities are going to be attenuated by the loop gain, including the nonlinearities that are coming from these capacitors. As long as there is loop gain, these nonlinearities are going to be reduced. The problem is that in any physical system you will always have more poles than zeros, which means that the loop gain will decrease and eventually become zero, meaning that there is not going to be loop gain, and then there is not going to be correction for nonlinearities. So nonlinearity correction will decrease with frequency, because at higher frequency you see that the gain it is going to drop, the loop gain is going to drop. So we will have to accept at some point that then nonlinearities will rise at higher frequencies, and we will have to check them very carefully if they are under specifications. But there is one very important situation that limits the linearity of an amplifier, and it is also related to the capacitor, and that is the slew rate. Okay, so there is typically in an amplifier one capacitor that defines the slew rate, the maximum rate at which the output can change. The voltage can change over time, and that it is basically because capacitor it is charged and discharged by a current source that we put in our design, and under large signal swing conditions this capacitor will not be charged at enough speed to be able to follow the signal, and that it is a mixture of speed of the signal and also amplitude of the signal. So we will have a really interesting example that shows this problem. So what we have is that when the amplifier is subject to a large signal at high frequency, it can be that one or several transistors leave the saturation region because of one capacitor cannot charge or discharge quickly enough. So basically one of several transistors will be switched off or will be totally on, working as a triode, as a resistor, and then as soon as one transistor is off or one transistor became a resistor, then the feedback loop is broken, and then all the correction that we have been talking about when we have a loop gain has to exist. The feedback loop, it is broken. So the best way to understand how this happens is to have an example, and then that is how we are going to show two examples. So the first example deals with the importance of biasing the output stage accurately, taking in consideration all the loading and the impact of doing it wrongly. And the second example deals with nonlinearities due to slew rate.